All right, today we're going to talk about our applications of quadratics, and these are ones that we're going to do by hand. And so quadratic equations are widely used in science, business, and engineering. They're commonly used in situations where two things are multiplied together and they both depend on the same variable. So what we're going to look at here is this first graph, and it says it represents the feet or height in feet, which is your y, of a golf ball after x seconds. So if you notice, time is your x, and then it says height is your y, and you've got your quadratic here, and here's the equation of the ball. So, or the path of the ball. So it says, what is the maximum height of the ball? So the maximum height would be at the maximum, and so if you notice, your height is your y value. So you're going to look at your vertex, but you're looking at your y value for that. And if you were to go here, here's your vertex, and kind of go just above 150. So we're going to say that's about 160 feet. All right. And then in this graph, your x-intercepts is where it crosses the x-axis. And that just represents when the ball is on the ground. So it's on the ground at 2 points when we started, and then when it landed. All right, now to come over here, we're looking at a graph that represents the height, so y in feet, of a rock being thrown off the roof over time, which is your x in seconds. So we started on the roof here at 100, and that's your y-intercept. So your y-intercept is the initial height that the rock was thrown from. Then, as it's thrown, it hits the ground right here at 6, and it says, when does it hit the ground? Well, we don't count this way because we don't have negative time. So we follow the path, and we look at the x-intercept, and right here is where the rock hits the ground, which is, we said, 6 seconds. So now let's look here, and we've got the graph models the distance underwater, which is y, in feet, as Blake tries to swim over time, which is x in seconds. So this is your x-axis here, here's your y-axis, and if you notice, this is 0 right here. So it says, what does the vertex mean? So this is the minimum, which is the deepest underwater that Blake went. So it's the time and distance. Blake is the deepest underwater. So this is the deepest point. And then the x-intercepts mean when he comes up to water. So he was up here at sea level or water level, and he was up here. So it's when he's at the surface of the water. Now let's go ahead, let's look at this one. So it says the graph below models the relationship between the ticket price of a concert and the expected profit. So here we have the ticket price in dollars, and then here for your y, we have the profit in dollars. So it says, at what price are the tickets the most profitable? Well, since this is the most profitable, you're going to look up here at your vertex, but we're going to look at our x value since this is the price. So we're looking at our x value of the vertex, which is $9. And so, and you know that's between the 8 and the 10 there. And then it says, what do the x-intercepts represent? So when you're here and when you're here for it crosses the x-axis, it's when no profit is being made. You're basically breaking even at this point. So there's no profit or more money from there. So make sure you get all that copied down. And then on this one, whenever we're solving, it's important to find the vertex. And we're going to look for the x value by doing the axis of symmetry. And remember, it's negative b over 2a is x. And then once we get x, we're going to plug it into the equation, and we're going to find y. And then to find the intercepts, we just set the equation equal to 0, and then solve for x using any method. All right, so let's go ahead, let's get started with this first one. It says, from the time that Mark Twain wrote The Celebrated Jumping Frog of Calaveras County in 1865, frog jumping competitions have been growing in popularity. So the function h of t equals negative 0.03 t squared plus 0.6t. And I wrote the plus 0 in there, it wasn't in there originally. models the height in feet of one frog's jump in t seconds. So we've got feet and we've got seconds. So if you notice here, it says, what's the frog's starting height? Well, there is no c value here. So your c value is +0. So that's your y-intercept. So that's at 0 feet. So if you're to draw this, here's where it began. And then the frog jumped and it landed. So you've got your time in seconds and your height in feet. And this is going to kind of help us understand what we're doing. So it wants to know when it hit the ground. So when it hit the ground would be right here. And that would be your x-intercept. So what we're going to do is you're going to set your equation equal to 0. And then what I did is I factored out a negative 0.03t because we'd like for that to be 1 or something that's easier to do. And then now that we got that equal, we factored this out of both of those. And so I got t equals 0 and t equals 20. So we're not going to necessarily use that one because that's when it started, but we want to know when it hit the ground. So this would be 20 right here, 20 seconds. All right, now we want to know when did the frog reach its maximum height. So maximum means we're looking at the vertex, and since it said when, we're looking at the x value. So we don't know what it is, so you have to find it by doing x equals negative b over 2a, and then plug in your information from your equation. And I've got x equals negative 0.6 over 2 times negative 0.03. And then if you enter all that in, you should have 10 seconds. So to get from here to here, this should be 10 seconds right there. All right, and then how high did the frog jump? I don't know why that's on there. That's weird. Okay. Okay, well, something's going on there. How high did the frog jump? So what we're looking for is we're looking for the vertex, but we're looking for the y value because that's the height. So you're looking here, and you would go to wherever the height is. That's if you have the graph. If you don't have the graph, we already found x. So we're going to take our equation, and instead of x, we're going to substitute in 10. So we wrote the equation, but we substituted 10 whenever we saw x. And then if you go ahead and simplify and solve all of that, you get the height is 3 feet. All right, so that's your information for all of that. Now for this next one, it says in baseball, the flight of the pop-up may be described using this equation where y gives the ball's height above the ground in feet as a function of time in seconds. So remember, your c value is your y-intercept. So we started at 96. Oops. And then we said it was 96 feet. Because that is your c value right here. So, and it said in feet, so that's why I put it there. All right. And then now I drew it here. So if you notice, I didn't start 96 here because 96 should be up here. This is 0. All right, so we're starting here, and then the pop-up fly goes, and it goes down like that. And then it says, when did the baseball hit the ground? So it's your x-intercept, which would be this point. So again, you're going to set your equation equal to 0. I factored out a negative 16. And then I went through and I factored those out, and I set those equal to 0. So I got t equals 6 and t equals negative 1. Well, we can't have the negative time, so that's why we're not using this one, but we are using that one. So when you're doing this, just be careful and make sure you check to see if your options make sense. All right, which would be 6 seconds. And then it's asking when did it reach its maximum height. So you're looking here, but you're going to be looking at your x value. So remember to use that, plug in your information, and you should have gotten 2.5 seconds. So this right here would be 2.5, which would be up there somewhere. And then now that we know what x is, we can substitute it into the equation to find y, which is the maximum height. So you're looking at your vertex, but we're looking for the y value now. So go ahead, substitute in everything, and you will end up getting 196 feet. All right. Now this one is kind of the same thing. You have an equation. We don't have a picture, but this one is a little weird because we're not talking height or distance and time. So it's cost in dollars of producing X number of computer chips. So I know your X are your chips. All right, so here we're looking for minimizes. It's still the vertex, but it just means it's going to be down, or it's going to be a minimum. So you're still looking for your vertex, just the X value. So you'd plug in all the information, and then you get 1 X equals 1 chip. And then if we want to know cost, well, we said cost in dollars is going to be your Y. So that is your vertex for the Y value. So you just substitute in 1 and then go ahead, and I'm going to round this to the nearest penny, which would be $34.99. All right, now this one's kind of a weird one because of how it's set up, but you have an amusement park charges $8 admission and averages 2,000 visitors per day. Survey shows that a $1 increase for the admission price, 100 fewer people would visit the park. So we need to figure out if it's $8 admission. We need to figure out how many people and the price to maximize the revenue. So the revenue would be your X. So what we're going to do is we're taking 8 plus your revenue, or plus a X, and then it averages 2,000, but it said here 100 fewer people would visit the park based on if there's an increase in the admission price. So we've got this here, we've got this here. You're going to go ahead and multiply it all out, combine like terms, and then I just switched the order. I put it in standard form. All right, now that you got that, this is your equation. Now we can determine the price to maximize the revenue. So here, all I did was negative b over 2a, and I just took from my equation, and I got equals 6. Well, if we were to plug in 6 here, you're going to get 14. All right, and then here it says at what price will the revenue, so that's what we're looking for, is the revenue, be equal to 0. So again, you're going to set this equal to 0. You're looking for your x-intercepts. I factored out a negative 100 and then factored that, and I got x equals 20 and x equals negative 8. So again, we're going to substitute that into here, and I've got 20 plus 8 equals 28, and then I've got negative 8 plus 8 equals 0. So those are so the prices where it'll be equal to 0 will be 28 and 0. All right. And now this one is kind of different because she's got fencing to make a rectangular dog pen. So that's what I drew here. However, a house is used for one side of the pen. So we don't need this side because that's part of the house. So really what we're doing is we're only looking at those sides. So we want to find the length and width for the maximum area. So your area is going to be, well, we're using the house 48 of fencing. So this whole thing is going to be perimeter-ish because we're not including that. So we're going to have this plus this plus this equal 48. So that means, that this side is actually 48 minus 2x because you have minus those two sides. So that's why this side is that. And then you go length times width, multiply those out, and you get that for your area is negative 2x plus 48x. So now to find our x, because this could be length or width, so we'll say this is width and this is your length. So once we solve, do negative b over 2a with this equation, you'll get 12. So your width is 12. And then now we're going to substitute in 12 to our original equation. And then you're going to get 48 minus 2 times 12, or negative 2. Oh, I'm sorry. Don't plug it in there. You're taking this and you're plugging it into here. So this guy is going to plug into there, and then that's where we got this from. All right, and then so that means the length is 24. All right, so these are some of the applications by hand. So you have to understand the vertex. If you're looking for the x or y, you have to understand the y-intercept, your x-intercepts. And then the only question that didn't really ask was how long is it in the air, but then you would just look at the distance of your x-intercepts. All right, and that is applications of quadratics by hand.